Yeah, so we would like to start with a very simple, it's a deterministic model as an example going forward. So it's something we have been familiar with, like something like this. You have SIR model, and then you have the birth rates, and then you also have the death. So in this case, the death and the birth are equal. So that's why you have mu bracket n minus x. So the rate at which people are coming in is the same rate at which people are going out. So that's why you have the mu to be the same, birth equal to death. And then you have the transmission rates. You also have the on the I class, on the I compartments, you have people who are coming in when they get when the transmission come. That's beta I s over n minus mu plus gamma, and then the RDT equals to um, lambda. I mean, sorry, gamma I minus mu r. So if you follow this particular um, diagram, it's the same thing like what we have there. Now, to begin, we will consider how to stochastically simulate the continuous time SIR model. That's equation 1 to 3 that we have there. How do we stochastically simulate that? Now, previously we considered stochastic simulation using discrete time models. An alternative to do continuous time stochastic simulation using an event-based approach. Now, the Gillespie exact algorithm and the tau leap approximation are methods we are going to be using because the theory of stochastic simulation and stochastic theory has not been stochastic theory has not been developed like ordinary differential equation. So there are not enough theorems to back up some of these. So instead of looking at theoretical aspects, we look more at the simulation, the quantitative aspect of it. Now, as discussed earlier, in earlier, the SER model and all simple models implies exponentially distributed waiting times between events. And that was what we said, like you find out that the infectious period is equal to 1 over recovery rate, and then the mu, which is the natural death, is equal to 1 over average lifespan. So the average lifespan is equal to 1 all over natural death rates. And then the infectious period is equal to 1 over recovery rate. So you are all of these, including even the bed and the transmission, follows an exponential distributed waiting time. So especially for ODEs. Now the Gillespie algorithm take advantage of this idea. If we, for example, consider how the SIR states of the SIR flows to change over time, we expect the following 6 possible changes. Now, if you look at the model, people are coming into from that model we have. Look at the model S. Let me first write it here. the model will be working on with. So you find out that from that model, if you look at X, that's the susceptible class. So you find out that X plus 1 at the rate mu n, mean that this particular parameter is being added to, is an addition. That is, the bet is an addition to the susceptible class, right? So that's why you have plus 1. Are you getting me? So you add plus 1 because there is something inflow into the susceptible class. Now, these are the 6 events. So event-based stochastic simulation. Now, the second event on that model is that on the S class again, people are moving out. So at what rate are people moving out? We are not, no. From the model, at what rate are people moving out? Eh? No. The first one. Eh? Mu S. Right. People are dying. So they are moving out. So that means S minus 1. So S move to X minus 1. As people die. As people as you are getting, people are being burned. You understand? S transform to S plus 1. You understand? And then the next one, the third event, is that what's the third one? On the S class now. What's the third one on the S class? Beta Si over what? N. So which is the transmission. So what is happening to them from the S class? They are moving out. So that's an outflow. Right? It's an outflow from where? So from infectious, from susceptible, right? And then they are being added to where? So at that point, S is transformed from S to S minus 1, right? And then I is transformed from I to what? Okay. Then the fourth event there, what's it saying? Mu I, right? So mu I is death. So from the I class, people die. So that's an outflow. So you have what? I minus 1, right? So, and then the fifth event is I equals to I minus 1, right? And then R equals to R plus 1. R is so you are having what? No, so for I, it's an outflow. For R, it's an inflow, right? So for I that's an outflow, you have minus 1. I minus 1. For R that's an inflow, you have what? And then R, which is the sixth event, what happened there? People die, so they recovered, died naturally, and then you are having an outflow, right? Okay. Are you clear with that? Now, thus, the system is expected to change by an overall sum rate of. Now we are adding all the events, 6 events. Now we have R equals to sum rates of R equals to mu n. That's mu n. That's the bet. Then plus mu s, which is the debt, plus BSIN, XI over N, which is the transmission, plus mu I, which is what? The debt from the infectious class, then gamma I, which is the recovered, and then mu R. So we can therefore draw a random exponential waiting time with mean R to update a continuous time clock. Then draw a random event from a multinomial distribution with probabilities given by the relative rates, and then we update the states variables accordingly and repeat it. Now, because of the many versions of compartmental models used in studying disease dynamics, it is useful to write a general stochastic simulator that can be applied to any set of rate of equations. So to this end, we define a R list. So what does that do? It gives us the list of equations corresponding to the rates for the 6 transitions of the SIR flows. Now we also have the quote. The quote is a formalism which allows us to set up the list such that all equations can be evaluated in a single S apply called the simulation progress. Now we are going to okay, let me just first talk about this and then we go to the simulation, the R platform to run. Now all of the first event is this, that's mu S plus I plus R, which is the bet. The second event is the mu S, which is susceptible death. The third event is the beta SI all over. That S plus I plus R is the total number, which is N, right? So it's the infection. And then the mu I is the infected deaths. Infected deaths. Now the gamma I is the recovery of the infectious. And then the mu R is the recovered death. Now we next define a transition matrix associated with each SIR event. So we are going to put up a matrix. Now the 3 columns correspond to changes in S, I, and R respectively. So the rows correspond to the 6 possible events. So we have the event says so we have 1, 0, 0. So the 1 represents the bet, which is coming into S, and then the other ones are 0 there. Then that's SIR. There's nothing coming at that point. So the next one is for the second event. You have -1, 0, 0. Nothing is coming for others. Then you have -1, 1, 0. Then that's for the transmission. Then you have -1, 0, 0. And then you have this. So maybe we go here. Okay. From here, we have so the transition matrix P is going to be, for this one, the bets. Now the S, the I, and the R. So the S only have something coming in, right? So we have 1. Nothing for, and that first event, nothing for others. Now the second event presented what? From S. So it's going to be what? -1, others 0, right? Then the next one. So you have something is going out of S, coming into I. So you have -1, 1, 0. Okay. And then the next one is nothing is happening here. And then this one, right? And then gamma, something is going out of I, right? But coming into, right? It's going to be like this, right? It's going out because it's recovered. So, and then going into R, right? And then the last one, right? So that's the matrix we'll be working on. Said? Okay, yeah, because it's death, right? It's death. So Moyo, maybe I'm sure, I don't know. Let's see how far I can go, but I may need my laptop after, but let's see when it's time. So now for that, we build that matrix, the matrix there. So we finally write a general purpose function to simulate a dynamical system using the Gillespie algorithm. So the idea here is to write a function that is sufficiently robust and general that it can be applied to events-based stochastic simulation of any model. So, like all of the model you have, some of you are working on a mathematical model. I mean, at the end, if we're able to finish this before Friday, you can begin to apply stochastic simulation, event-based stochastic simulation to your work and see how it come out. We can have another example. Maybe we'll draw another example here now, and then we'll do it together. Now, the function takes 5 arguments to accomplish this. Now, so you have the rates. So a list of rate equations corresponding to each of the possible, that is events, possible event using the quotes formalism. So the event matrix is a E by S matrix of changes to each of the states, S state, variables associated with each event. Then we have the parameters, a vector of parameter values. Then we have the initial vals. So initial vals talk about a vector of initial values for the S state. Then we have the norm events, number of events to be simulated. And then we have this kind of code, but we'll go back to the R now if we're able to, but I'm going to give another example. Now, if I have is it? Oh yeah, thank you. Okay, something small like this. So now we have the susceptible human class, and then what is going on here? The events. We have different events here, right? So we have births who are being born into this class at this rate, lambda age, and then we have probability of transmission, right? And then we have the contact file, and then IV, which is mosquito, infected mosquito coming to human, right? So this one does not have any control. It's just a normal malaria model. And then you have mu H, people are dying naturally, and then people who are treated in the people who are infected and infectious, they are treated, they go back here, they come back because there is no transmission blocking vaccine. So you get back to susceptible even after treatment. And then the pre-infectious lab, which is exposed, you have people from here. This is another event. They come in, and then the progression. People progress from the pre-infectious class after some days, to either infected and infectious class or to the asymptomatic. So if they move here at this probability P alpha H EH minus theta H plus M. Theta there is a disease induced death. That means you can die due to the disease. This mu H is a natural death. And then you have the asymptomatic. People can move from the exposed to either infected and infectious, and then to the AH. So P, the P there is the probability between 0 and 1, right? So it means that if P is 0.5, it means this is 50%, and then this is 0.5, 50% as well. So it means that 50% may come here, and then 50% comes there. But most times it's either 20-80. So most times the asymptomatic are 80% of the population. So minus the rate at which people die, said alpha H, the rate of progression from the exposed. So, and then you have the susceptible mosquitoes. That's female anomaly mosquitoes. They are being born into the class, and then that's lambda B minus the rate at which this probability, and then the contact between a human infected and infectious human, and then the susceptible mosquitoes. Then plus this it's like a reduction factor, because the rate at which asymptomatic is going to infect the susceptible mosquito is not the same rate as the IH will infect the susceptible mosquito. So we are factoring in this Q there, and then beta VH file AHSV NH, and then minus mu V, that's the natural death rate of the susceptible mosquito. And then all of these guys, they come here from the susceptible class, they enter the pre-infectious. And then from the infectious, you have the progression, alpha V plus mu V. The mu V there is the death. The alpha V is the progression from the pre-infectious to the infected and infectious female anaphylaxis mosquito. Now, what are we doing here? We want to create our matrix. After the on which one? On the SB class, second to the last. So that's minus alpha V plus mu V EV. So we will do it together now that we are moving up gradually. So for the first class, we have how many events? For SH is being transformed into SH plus 1. So how is SH being added to? By bets. So by beds, standard age by beds. Okay. Now, is there any other addition? Huh? So not only beds, yes, by what? So that is people who 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 become susceptible afterwards, after recovery due to treatment, right? So we have this SH plus 1 again. So, and then that one will be a negative for the other class. So, and then we have SH minus 1. What are the things that give us SH minus 1? This, right? So you have this, which is a beta H. So we should also add IH minus 1 here, because this M is coming from here, right? So we are going to have, so for here we have beta V H, HV, IV, SH. So it's going out of this last by minus, but it's coming into here. So EH will be what? Plus 1, right? And then mu H also. So at the rate mu H SH, we are having negative. Then for EH is being added to. So I think we have written that. We have written one of it. H. So we have EH minus 1, which is alpha. That's alpha H plus mu H. Alpha H plus mu H. At that rate, that's the events. Yes, so then IH is as IH plus 1 alpha H EH, right? That's the only addition. Second one is IH. No, it's only this. Huh? So you have IH minus 1, which is what? Theta H plus mu H, right? So, and then we have AH. That's what? AH plus 1 minus P alpha H EH, and then AH H minus 1 mu H AH. And then we have SV transform to SV plus 1 is lambda V, right? Then SV minus 1 is going to be these two. BH IH SV plus Q by SV all over N, and mu V, right? Rate at which is going out. So, and then we have EV. So this one is EV, that's EV. Okay, so okay, this one will be also EV plus 1, right? EV plus 1. So we only have EV, then EV minus 1. It's going to be alpha V plus mu V. And then IV is going to be that's IV plus 1 will be alpha V, right? And then IV minus 1 will be what? Mu V. Okay. No, because there is relationship. Like SV, right? SV minus 1, right? So this one is relating to 2. Like you can have SV minus 1 and EV plus 1. EV minus 1. There's no what? Yeah, that it doesn't mean. It does the event. The event is saying transmission, right? The event here is saying death. I just didn't add this is death. Okay, so it should be EV. Yeah, it's an event. It's supposed to be like that. So each of those events, so this is event. Wait, so we have different kind of event here, right? So starting from SH plus 1, it's an event. People are entering the class. They are entering the susceptible class via bats, right? Via beds. Are we getting it? And then people are also entering via loss of being susceptible due to after recovery with M. So they enter the class, and then so the relationship now comes in where for this is plus, for this is minus because it's going out of I, right? And it's moving into X. Now the other one for S is that there is an outflow. People are going out. So people go out from S due to transmission, right? So you have this. You have the transmission, and then people are coming into the pre-infectious class, right? Due to that transmission, you have this. So for susceptible is minus, for exposed is what? It's plus. So and then the mu H is also there. So people go out of that class and then they come in. And then this other one, you have EH. People are going out of the exposed or the pre-infectious class. Yeah, at this rate, alpha H minus plus mu H. Sorry. So and then for IH, you find out that people are coming in at this rate. And then you have this IH. For IH again, people are going out. They are going out due to this event theta H plus mu H. Theta H plus mu H. That theta H there is disease-induced death, and then mu H is natural death. Now, AH, asymptomatic. People are entering the asymptomatic due to this probability. You know, probability of some people going from the exposed. Some either go to the infectious class, or some percentage goes to what? The asymptomatic. So, and that's what we have here. And then the AH also, people go out of AH due to death and natural death. And then SV, people come into the susceptible female anopheles mosquito class due to birth. And then that is lambda V, which is the birth rate. And then people go out. They leave their class when they are infected. They are no longer susceptible. You understand? They are no longer vulnerable. They are infected with Plasmodium falciparum. Sorry, that's the female Anopheles mosquito. So they move out, and then they move out of SV, so making SV to have an outflow, right? That's an outflow. And then EV is having an outflow. Yes, there is an outflow there, but also for that transmission, that event, there are two things the event is doing. There are two classes the event is affecting. This event transmission is affecting both the SV and the EV. Now, in that, from the SV, certain number are leaving. They are moving to where? EV. So for EV is an inflow. For SV is what? An outflow. So mu V SV. That's what? An outflow for what? For SV. So then we go to EV. EV minus 1. So means that there is an outflow for EV, which is alpha V plus mu V, right? And then this one is an inflow for IV, which is the infectious class of the mosquito, female Anopheles mosquito, which is alpha V EV. And then the last one there, you have IV, which is IV minus 1, mu V, right? Mu V IV, right? So you are good to go. Now, I want us to do the matrix. Can we do the matrix? So how many events we have? Let's count the number of events we have. Yes, I'm coming. Yes. Yes. Eh? Yes. There are some. Take for instance now. Can we come here? Can you please give me the slide? Now, okay. So you find out that there are some that you have. Take for instance, x plus 1, right? X plus 1 is people are being born, right? And then x minus 1 is that at certain rates, people are going out, they are dying. Now, on the other class, you have you will see that these two are joined together, beta SI, because in that class, for susceptible, it's negative, it's going out. For infectious, is what? It's coming in. So that's why we are having this kind of event joined together there. And then for this other class, I minus 1, the next one in the I class, what happens? People are what? They are leaving. So you also have here two things joining two classes together. So if you have an event that joins two classes together, you have to bring them together. Are you getting what I'm saying now? So what we are looking for are the events. How many events do we have in a particular model? So if you count the events, you don't count one twice. You understand? We have only one transmission. It will appear twice. Maybe some as outflow, some as what? Inflow. So but you have to make it one, and then you have two matrices. For that, so one will be plus 1, and the other will be what? Minus 1. Are you get what I'm saying now? For this particular matrix now, how many events do we think we have? 14. 12. Don't repeat one twice. You have repeated once 2 times. 12 events. So for those 12 events, you are going to have 12 by 12. 12, sorry. Is it 12 by 12 now? I don't know. So maybe 12, 12 by 7 matrix. So, I mean, I don't know. It's my, do I see that time? Oh, okay. So, you have to develop this and then we'll come back to it. Yes? Which one? This one? IH plus QBB 5 AHSV, right? Eh? And mu VSV. This one. Oh, okay. Yeah. Okay. So, okay, what will have happened is this. Sorry, maybe. Maybe I'll for EV plus E for EV, right? EV, right? We are going to have let me just bring this one here. We are going to have SV minus 1 and EV plus 1, right? Due to BVH 5 IH SB plus QBVH 5 AH SB all over NH. So maybe for better clarity. So this one we only have mu V, right? Do you understand? So as in this event is for both. So one will be minus 1, one will be plus 1 for this event. Do you understand? You have one event here. This event, one is going out of S, and then the other one is coming into E. So it's affecting two classes, but it's just one event. So the one event will affect two classes when it comes to transmission, or maybe recovered. It depends. So this event now is affecting two classes. So in one class, it is going out. In the other one, it is what? Coming in. So when you are doing the matrix is going to be minus 1 and what? And 1. Minus 1 for what? For SV. Plus 1 for what? So the number of classes we have in this model is how many classes we have? 7. So that's why we have 12 by 7. Right? Okay, we continue from there. Thank you.